So we will continue from the PN junction, which we were trying to discuss. So we have spoken about the P type of semiconductor and the N type of semiconductor. And as I told you that we form a PN junction diode by combining a P region and N region by certain fabrication techniques, which we do not have to study in our syllabus. So it's not that you just get a P semiconductor and a N semiconductor and keep it in contact with each other. Then a PN junction will be formed. There are certain fabrication techniques which you will study in uh, higher subjects of electronics if anyone takes that particular branch. And study of PN junction diode is very important because the PN junction forms one of the basic blocks of all further electronic circuits. Some of them are like transistors, which are used for amplification, which are used for electronic switching. Okay, and various other devices. As you go ahead, you will study in higher physics branches all these different semiconductor devices. So that's why study of the PN junction diode is very crucial for that analysis. So what will happen when you take a P region and an N region? Now let us say that at time t equal to 0, I have a scenario here where this is the P region and this is the N region. So we know that P type semiconductor means large number of holes. So can I write here holes everywhere? And in addition to holes, there will also be certain electrons, but very small in number. How did the electrons get in here? Because there is always thermal generation which is happening. If you talk from the viewpoint of your valence band and conduction band, which are separated by a certain band gap, we know that certain electrons in the valence band, if they get sufficient energy at room temperature, okay, room temperature, we can say 27 degrees centigrade, then they can cross over this energy band and come to the conduction band. And that's basically going to leave around holes. Okay, so there are two ways in which holes can be formed in the P junction. One is because of the impurities, and the second is because of thermal generation pair. And some electrons are going to come in the conduction band, which are very going to be less in number. So that is why here I will just write 1e, and this 1e which I'm writing here represents the thermally generated electron in this way. Similarly, if you talk about the N-type semiconductor, it will be primarily formed of the majority carriers, which are electrons, because of adding a pentavalent impurity. But because of the thermal generation, there are going to be some few holes which are there on this side also. So I will write just one H on the right hand side. All right. I hope this part is clear, Mohit, what we have drawn here. Please let me know whether this diagram is all right. Okay, now we have a scenario which is going to be something similar to what you find in gases. In gases, we have studied this concept called as diffusion of gases. So when does diffusion of gas take place? When you have a particular region in the room, let's say if there is a higher concentration of a particular gas, and in the other part of the room, there is a lesser concentration of gas, then we know that the gas molecules over a long period of time, they will be diffusing and you will have uniform distribution throughout the room. So there is going to be diffusion always taking place from higher concentration to lower concentration. So you have a similar scenario here that on the left hand side here, you have a large number of holes, and on the right hand side, you have very less number of holes. So there is going to be a diffusion of holes from the p side to the n side. And similar type of diffusion will also happen to the electrons. So electrons on the right hand side are larger in number, so they will diffuse towards the p side. Okay, so that's what we have written here. Electrons diffuse from the n side to the p side, and similarly you can say that holes diffuse from the p side to the n side. Okay, Sarthak, are we on the correct track here in understanding things? Okay, so diffusion, we have all understood this one. But there is one important difference. Do you think that these holes and these electrons, they're going to combine and then just, both of them are going to vanish? Is that what is going to happen here? What do you feel like? Uh, See, there are two types. See, whenever hole travels from left to right, okay, so Harsh is saying no. So when hole travels from left to right, the direction of current is same as the direction of the holes. Okay, it's a positive charge. So you can say that the hole current, which I can write as IH, okay, is going to be towards the right. And electron, which moves from the N region to the P region, okay, electron direction is not the direction of the current. Current is always in the direction opposite to the direction of the electron flow. So the direction due to the current due to the electrons are also going to be towards the same direction only. So it's not that both of them are going to cancel each other. Okay, and the combination of both of this is what we call as the diffusion current. Okay, it's an I here. So diffusion current can be written as a combination of the current due to the holes crossing the junction plus the current due to the electrons crossing the junction, both of which giving rise to current in the same direction, that is from the left to your right, from the P region to the N region. Now, one difference here, which is to be noted, that when holes are traveling, in reality, who's moving? Are holes moving or are electrons moving? That's one important thing to comprehend and think about it. They are electrons moving. Okay, we have seen that at length even previously. Electrons are moving, but which electrons are moving? Are the free electrons moving, or the electrons at the valence band, are they moving? So those electrons, are they same as these electrons, or it's something else? That's another point to be differentiated, because you said that holes moving from left to right is actually movement of electrons from right to left. Okay, in reality actually it's this one. Then are these electrons what I'm showing here, or are they some other electrons? Maybe you can share your views here. Okay, so no, sure, electrons of the n region नहीं है. n region ठीक है, but n region में कौन से? देखो, दो electrons होते हैं. एक electrons होते हैं जो valence band में रह सकते हैं, उनको हम कहते हैं free electrons. और दूसरे electrons जो है वो valence band में है. तो वैलेंस बैंड का इलेक्ट्रॉन का मूवमेंट, होल का मूवमेंट कहला जा रहा है, या जो इलेक्ट्रॉन्स फ्री इलेक्ट्रॉन्स है उनके कारण जो मूवमेंट है वो होल करंट है? शर्वरी, फ्री इलेक्ट्रॉन्स है क्या? नहीं नहीं, फ्री नहीं है. ये देखो, यहां पे पीछे जाएंगे, जरा क्लैरिटी आप देख लो. यहां पे आपको याद रहेगा कि ये जो होल का जो मूवमेंट रहता है ये किसके कारण होता है? बिकॉज ये जो ट्राइवेलेंट इंप्योरिटी आपने ऐड कर लिया, देयर इज अ वेकेंसी, एंड द अदर इलेक्ट्रॉन्स which are quite stable here, as I told you on the last Sunday also, thinking that the grass on the other side is green. Okay, they think that okay, maybe that is a better place for me to be there. So these electrons, they live their stable bonding and they go to the hole here, and that leaves a hole behind. So hole has moved from here to here, but actually it's electron moving from here to here. Now which electron is this? This is not a free electron. It's not a free electron. These are the bound electrons which are moving. Please note that carefully. Is it all right? Okay, so that is understood. Fine. So coming back to where we were. So the holes which are moving from left to right are actually electrons from where? From the valence band. That's one important thing to be understood. Okay, so that's why we are adding this separately. ये दोनों अलग अलग electrons के कारण है, ये same electron के कारण नहीं है. Okay, so you can take down this slide before we go to the next one. Okay. So here also I've shown that same thing about diffusion. So there is a larger concentration of holes here, and naturally we will expect that the holes will move towards the lower concentration region. Okay, and the same thing what I spoke about in the last slide I've written here. Physically, this movement of holes is actually movement of the valence electrons on the n side. Okay, which are trying to fill up the vacancies or what you call as the holes on the p side. Okay, so that's a point which we tried to explain in the last slide also. So movement of the holes physically represents the movement of not the free electrons. Okay, so not the free electrons, but their movement of the valence electrons on the p side. And same thing is valid even for the n side. Because of the concentration gradient, the electrons are going to diffuse onto the p side. Now, how long will this diffusion take place? Will this diffusion continue and completely occupy the n and p region, or will it stop somewhere? What is your opinion? These are the holes, so all these holes will go there, and all these electrons will go to the left hand side. They will diffuse. So is that going to happen, or it's going to happen only for a localized region? Maybe some of you who can recollect this part. It will stop after some time is the comment coming up here. So we will have to see that why does this diffusion stop after some time? Okay, so the current will slow down. Okay, now if it's going to stop after some time, what could be the reason for the stopping? Why doesn't the diffusion take place completely? Why only over a certain region it goes, and then further diffusion is prevented? Stop after some time का क्या मतलब है? Diffusion बाद में prevent होता है, तो prevent क्यों होगा फिर? उसका कोई रीजन हम सोच सकते हैं. Okay, so depletion region is created, it seems, and therefore there is an electric field. Okay, so let's have a look at that part then. Okay, so here we will say here that when you talk about the p-n junction, the p and the n, okay, so these are the electrons and these are the holes. I've just showed 2 and 2 here. And you know that when you add a pentavalent impurity, then having given up this extra electron, we know that the donor becomes which type of ion? Positive ion or negative ion? It's giving an electron, the pentavalent impurity, 5 electrons, na? Like arsenic and all those impurities which are called pentavalent impurities. They will give an electron and then they will become a positive ion. Okay, so here you have positive ions also, which I had not drawn in the previous diagram. Okay, you have some positive ions also. Of course, they will be less in number because the donors which you have added, They are very less in number. It's 1 part per million. Okay, we had done a sum on that also last time. Very less number. And similarly, so here I'll write here, donor becomes a positive ion. Okay, and here in the whole P region, you're going to add a trivalent impurity, isn't it? And in a trivalent impurity, we know that there is a deficiency of an electron in one of the covalent bonds. So it accepts an electron from somewhere else, and a hole is created because of that. So here I can say that because of accepting an electron, the donor becomes a negative ion. Okay, so I hope this line thought of line process is all right. So donor in the pentavalent side becomes a positive ion, and donor here in the trivalent, the P side becomes a negative ion. So here you have your negative ions. Okay, now uh, this is a junction. Okay, this region which is separating both the P and the N sides, it's called as a junction. So the as we saw, there is going to be diffusion of the holes on the right and diffusion of electrons towards the left. So this region, which I am going to show now, which is at the boundary, is going to get depleted of the free carriers. Okay, because these electrons here, which are the free carriers, they are going to go towards the left. So it's going to leave behind what? It's going to leave behind uncompensated ions. Please understand that prior to forming the junction, the right side as well as the left side are electrically neutral. The number of positive charges is equal to the number of negative charges. But after the diffusion has occurred, on the right hand side, you can see electrons are gone away. Okay, so once the electron goes away, what's left behind are the immobile positive ions at this junction. And similarly, on the left side, what is left behind is the negative donor ions, which are immobile. Donor ions, they can't move. They're immobile in nature. So they will remain there at the junction. Okay, so now you can see that here you have a positive charge and here you have a negative charge. Okay, so that means that there is going to be an electric field that is going to be generated at the junction in the direction that I'm showing in the diagram. So once this electric field gets generated, how will the diffusion process be affected by this electric field? You can just try to visualize what's going to happen now. What's going to happen to the holes? Can the holes peacefully move to the end side because of this electric field, which is pointing towards the left? Certainly not, because holes always get accelerated in the direction of electric field. So the holes cannot further diffuse towards the end side. And similarly, we know that the electrons on this side will experience a force in a direction opposite to the electric field. So how can they move in the direction of electric field? So that means that diffusion process is stopped. Is that thought of line process all right? Ninad? Okay, so let's first take a reading before we go ahead. So here I am saying that when the electron diffuses from the N to the P side, it leaves behind an ionized donor, as I've shown here. And similarly, there is a positive, this is a positively charged one. And similarly, on the other side also, there is going to be a charge, which is going to be generated out here. So this region is what we call as the depletion region, because it is depleted of all the free charges. Okay, chalo. So you can take this down and let's go ahead in our discussion. So certain things which I have explained will be there here. Holes will also diffuse, and that's going to leave behind a negative charge. We have seen that. And what's going to happen is that this diffusion is going to make the n side, which was previously, it was electrically neutral, but now it's not going to be electrically neutral. It's going to be positively charged because of these donor ions. And similarly, the p side was previously also electrically neutral, but now it's going to be negatively charged because of these ions, acceptor ions. ओके, चलो इसके बाद इस रीजन को हम कहते हैं डिप्लीशन रीजन, और ये जो डिप्लीशन रीजन का जो थिकनेस है, it is generally of the order of 1/10 a micrometer. It's a very small thickness. Okay, a very very small thickness over which this electric field is developed, and which further stops the diffusion process. So we can say that at time t equal to 0, when you combine the p and the n junctions, the diffusion current was maximum. Okay, and at time t equal to infinity, how much will we put the diffusion current to be? Can anyone comment? At time t equal to infinity, how much is the diffusion current? Almost zero. Okay, so that's a very okay. Why you are saying almost and not zero? What is the reason behind that? Why not zero? Why approximately zero, almost zero? You all have used it. That is correct actually, but why you have not written zero? Some of the holes and electrons do move. Okay, so it's something like this, that though you're having this depletion region in this way, नो नो, ड्रिफ्ट करंट अलग है. ड्रिफ्ट करंट नहीं, मैं पहले डिफ्यूजन करंट के बारे में बात कर रहा हूं. ओके, ड्रिफ्ट करंट विल सी दैट लेटर, मोहित. Diffusion current is not zero, but it is approximately zero, I'm saying. Okay, it's not equal to zero, मैं नहीं लिख रहा हूं. And the reason for that is there are always going to be some holes and some electrons here having higher kinetic energy. And those electrons and holes will not be stopped by the electric field. Okay, so if you are having sufficient kinetic energy, we saw the same type of experiment in even in modern physics, correct? Like photoelectric effect में भी हमने retardation दिया था. Retardation का मतलब ये नहीं कि electrons जा नहीं सकते, आपका stopping tendency हो गया है बस. But there are always going to be some holes and electrons having higher kinetic energy, which can always cross the depletion region. So that is why the diffusion current is approximately zero, but not equal to zero. Okay, so chota value rahega, chota current. This is all right, Kritika? That why the diffusion current is approximately zero, but not zero? Okay, now we have to understand whether is there any other current which is existing in this particular diode. Okay, so let's try to analyze that. If you take this PN junction, you can see that in this P junction, we will always have some electrons also, which are going to be free electrons, though less in number. And similarly, this n region are always going to have some few holes which are going to be less in number compared to the electrons. What are these charges called as? There is a name for those charges. What is the name of those charges? Electrons in p region and holes in the n region. Anyone knows their name? Minority, correct. Minority carriers. And minority carriers are generated due to what? Where did they come from? कहाँ से आए वो? Who's the source? Thermal generation, na? At room temperature, there is always going to be some amount of thermal generation where some electrons will go to the conduction band and live behind the holes. So there are always going to be such type of carriers which are called as the minority carriers. Now, if you talk about these minority carriers, you can see even I have drawn it in the P and N region, but even if you talk about in the depletion region, okay, even in the depletion region, you are going to have continuously these electron hole pairs generated. यहाँ पे भी generate होगा इस region में thermal generation के कारण, and this electric field, what it will do is that it will try to accelerate these electrons towards the right, because electrons will get accelerated in a direction opposite to the electric field, and these holes will get accelerated in the direction of the electric field. So holes will be going towards the left and electrons will be going towards the right. So it constitutes effectively a current which is going towards the left, and this current is what we call as the drift current. Okay, drifting because of whom? Drifting because of the electric field. So here the thermally generated carriers are going to be pushed by the electric field, and all the holes will come here and all the electrons will come here, and it will ensure that this region is depleted of all free charges. So when you keep a semiconductor in your cupboard, then I will say that at equilibrium, how will we compare the magnitude of the diffusion current and drift current? What would be their relation? Diffusion current and drift current. How will they be related? Will it be greater, it will be less, or will it be equal? क्या लग रहा है इनमें से? When you are keeping it inside the cupboard, cupboard का मतलब है you have not applied any potential whatsoever. You have not applied any external biasing to your PN junction. So how do you expect these magnitudes to compare? देखो, diffusion current and drift current are exactly opposite in direction. Please note that because diffusion current is because of the holes here going to the right. So diffusion current is towards the right, and drift current, as I've shown here, is towards the left. No, it is not. This is not true. Diffusion current is greater than drift current is not true. When you're keeping it inside the cupboard, you cannot have any net current. Net current has to be zero because you have not done any biasing. So therefore the diffusion current has to be equal to the drift current. Only then I can say that the net current in such a PN junction is zero when it is kept inside the cupboard. Okay, is that acceptable? Sharvari? Greater than, आपको क्यों लग रहा है कि ग्रेटर देन होगा? ओके, क्लियर है ना? चलो, so now let's try to see whatever things I have listed out here. Some points I will put forward in the future slides here. So we are saying here that due to the positive charge, positive space charge on the inside, an electric field is going to develop, as we have explained in the previous slide. There is going to be an electric field that is going to be generated, and due to this electric field, any thermally generated carrier that is inside the depletion region, which is also called as the space charge region, it gets pushed on either side, and therefore this region is going to be depleted of all free charges. Okay, and this current, which we are going to talk about, the next current is the drift current. And the drift current, as we saw, is because of the electrons on the p side moving towards the n side, and the holes on the n side moving towards the p side. That is the drift current. And we also saw that the drift current is opposite in direction to the diffusion current. Okay, so some few things which we had explained in the previous slide are put forward here. You can just take a screenshot of this. So we are trying to summarize all that explanation in one diagram here. The electron diffusion happening towards the left, the hole diffusion happening towards the right, both of them constituting the diffusion current towards the left. And similarly, in this depletion region, whatever electron hole pairs are formed, this electric field, which I'm showing here, is going to push the holes towards this side. So hole drift is going to be towards the left, and electron drift is going to be towards the right. So effectively, we can say that your drift current is going to be towards the left. Okay, so they are in opposite directions. And as I told before, that the diffusion current is going to be equal to the drift current without any biasing. Biasing means applying some voltage supply. So you don't apply any power supply to this PN junction, then that's what you mean by no biasing. So are things clear up to here, Aryan? Aryan? Okay, clear, no? Okay, wait. Let me just quickly take the attendance. Okay, let's go ahead then, if things are clear. Uh, yeah, so this also you can just take a screenshot. I have already explained this, that there is no net current when you're keeping a PN junction diode without any biasing. There's a lot of theory in this chapter, so it's just we have to take a lot of reading here. And I think the best textbook for referring for this particular chapter would be your CBSE textbook. They have done a very good work in explaining all the details in a very simple and lucid manner. So you can refer to this one, and along with that, you can also club your HC Verma along with it, because you will of course require HC Verma also. But I think some things are there which are very nicely explained in the CBSE textbook and more and elaborate than HC Verma also, certain important details. Okay, so you can always get a soft copy of this in case you don't have it, and you can read from there. Okay, so we can say that when you are having a PN junction, because of the formation of this depletion region and the resultant electric field from right to left, we know that in the direction of electric field, what happens to the potential, Danpreet? Now, your electric field is directed from right to left. So, what happens to the potential from right to left? Can Danpreet tell me that? From the N region to the P region, the electric field is oriented. And we know that the potential always decreases in the direction of the electric field. So that means that here in this depletion region, your potential is going to decrease. And therefore, we can say that another way of saying that why diffusion does not happen is that this potential barrier, it's called as the barrier potential. This potential barrier basically tends to prevent the movement of the uh, majority carriers from the P to the N and from the N to the P. ओके सो इसको हम बोलते हैं बैरियर पोटेंशियल और इसको हम ऐसे दिखा सकते हैं लाइक दिस. यहां पे पोटेंशियल हायर है और यहां पे पोटेंशियल लोअर है और ये जो पोटेंशियल डिफरेंस होगा इसको हम बोलते हैं बैरियर पोटेंशियल. So if you want the diffusion to happen, then what should you do then? So that the whole process of diffusion will start up again and some net current will flow, because currently diffusion current is equal to the this one drift current. So as one student is rightly saying here, if you overcome this potential barrier or if you decrease this potential barrier, then the process of diffusion can once again start. Okay, so let's see that after we log in back. So let's quickly come back again.